Howdy, today I will be solving the third exam for Physics 207, 2009 to hopefully help you prepare for the exam. So let's get started. So for the first question, we have a very long wire that carries a current I, and it has like three segments essentially. We have two straight segments which are very close together, so we're going to assume that they're like essentially here, and it's just for the picture just for us to see like what's actually happening. And we have a circular region with radius r. And what I want us to find is, or at least for the first part, I want us to find the magnetic field due to the circular part of the wire at a point P, which is the center of a circle. And in this case, we're not dealing with infinite length wires or a solenoid, which is a coil. So what we're going to use is Biot-Savart's law, which is dB is equal to mu naught I over 4 pi ds cross r divided by r cubed. And I believe these are given at the fronts. Yeah, it's right here. So that's one we're going to use. And we're going to start with the circular segment. So ds is the length, right? Not to get it confused with area. So ds goes in the direction of the current. So if I say, let's choose this point. So if I say this is ds, r points from where I'm starting to the point of interest. So my r vector will be here. So then I would get that dB is equal to mu naught I over 4 pi ds cross r. So if I put my palm on ds, I curl my fingers towards r, I would get ds r, where r is the radius of the circle, which will be r, big R, divided by r cubed, and it would be pointing out of the page. Because if I put my palm on ds, I curl my fingers towards r, my thumb is pointing up, so my magnetic field is out of the page. So now to find the magnetic field, I would have to integrate both sides. So the magnetic field would be I can pull out the constants, so it'll be mu naught I over 4 pi r divided by r cubed is r squared, and then the integral of ds, where ds would be the length, and this is a full circle, so that's just a circumference, so that's 2 pi r. So this is equal to mu naught I over 4 pi r squared times 2 pi r, which simplifies to mu naught I over 2r. And this is still out of the page. So that would be the answer for the first part. Second part, it wants a magnetic field at the same point of interest due to the rest of the wire. So if we look at the wires closely now, and I choose this portion as my ds, right? My ds will be pointing along this way, right? And my r vector would also be pointing, my r vector would also be pointing this way. So the cross product of these two vectors would be 0, right? Similarly, if I do the other wire, my ds vector will be the direction of the current. So ds is this way, and my r vector is this way. They're still parallel. Even though they're going in the opposite direction, ds is still parallel to dr, so the cross product of this is going to be 0. So the magnetic field for both of these wires would be 0, and you can write something like ds cross r is equal to 0, or you can say r parallel. So the only magnetic field created at this point is in the circle. So now for part C, it's a completely different question. Particle with a mass m and charge q. So let me draw that out. Particle with mass m has a charge q moving in the positive x direction with a velocity of magnitude v naught. So it's going this way, right? Positive x, v naught. Ignoring gravity, if there were an electric field in the positive y direction with magnitude e naught, find a magnetic field that could be added so the particle velocity would be unchanged. In other words, find a magnetic field that can be added so the forces cancel out. So if I draw this, like just to represent the forces, I have my electric field pointing up, and the force of an electric field is QE, right? So I have QE up here. And then I want to cancel it, so I need a force, the magnetic force, to be going down. Otherwise, we won't be able to satisfy what it wants, which is the velocity remain unchanged. So recall that the force magnetic is equal to Q V cross B, right? And to determine the direction for B, whether it's in or out, we will need to essentially like trial and error to see if B is going to go into the page or out of the page. So if I assume that B, so let me write this here. Assume B is into the page, it's V cross B, right? So V, if I put my palm along V, so let me draw that actually. So if I put my palms along V, I curl my fingers into the page, my thumb will be pointing up, meaning the force would be up, and that's wrong, because we want the force to go down, cancel the force, the electric force up, right? So this is wrong. So let's try the other way now. So what if the B field is out of the page? So I put my palm on the velocity vector, and I curl my fingers out of the page. Again, my thumb is pointing down, meaning that the force is going down. So that's what we want. So B is out of the page. So B is out, and so this would be, it would be 90 degrees, so it would be QVB, where B is out. So then I would just set them equal to each other. So QE needs to equal to QVB, right? Because I need the forces to cancel out. Q's drop, so B is equal to E over V, and we already said it's out of the page. Right? And velocity and B are always going to be 90 degrees in this case. So that's why I technically said sine theta, but sine of 90 is just 1. So it's just QVB. And then again, B is out of the page because we need the force to be pointing down. And that's the direction of B that gives us V cross B down. Okay. So for this one, where's the one? A long wire has a current I, which is uniformly spread, which is very important to know, over its cross section. It has a radius h, so this circular wire has a radius h. A second very long thin wire is placed a distance w from the first wire. It also has a current I in the same direction, so they're both into the page. And it wants us to find the magnetic field by the first wire everywhere, where the first wire is a circular one. So whenever we see like everywhere, pretty much, magnetic field, or when we're given current and we want to find magnetic field, it's a good indication we're going to use Ampe's law, or Ampere's law, which is the B dot dr along a closed loop is equal to mu naught I enclosed. So current enclosed. And since for this first wire it's uniformly spread, we also need to know charge density, which is J equals I over A. So let's find the magnetic field everywhere, which in this case is just two regions. And you can think of it as Gauss's law pretty much for like magnetic fields. So my first region will be if R is less than the radius h. So I'm in here. So then the dr is just a little segment of this circle loop that I created. So I want the whole thing, it would just be b 2 pi r is equal to mu naught, and then it's going to be the current divided by the total area of this wire, which the area of a circle is pi r squared. Excuse me, but this has a radius of h, so it's pi h squared, times the area of our loop that we created. So that'll be pi r squared, right? So it's like Gauss's law pretty much when we had like charge uniformly spread. So this is mu naught times current over actual area. Actual area, which is the total area of the thing, of the wire, times our area, where our area is the area by the loop we created. So we can just simplify this. See what simplifies. So pi's cancel, one of the r's drop, and that should be it. So b is equal to mu naught I r divided by 2 pi h squared. So that'd be for the first region. Now for the second region where r is greater than h, let's do it in red. I'm out here now. So I have the same thing on the left side. B 2 pi r is equal to mu naught I divided by the area of the whole wire, which is pi h squared, times the area of where our loop is at. So our loop in this case is bigger than the actual wire. So anything past the actual area of the wire is like empty space. So the max area that we can have is pi h squared. Right, because we can't magically just make the wire bigger. It has a max area of pi h squared, where outside of it, so our area is still going to be pi h squared. Which is good, because then these two cancel. So then we're left with b 2 pi r equals mu naught I, or b is equal to mu naught I divided by 2 pi r. And then the second question, it wants us to find all points where the total magnetic field is 0. So to do that, we're going to have to also find the magnetic field of this wire. So it's just a wire. So if I create a loop out here, I will get that b 2 pi r equals mu naught I, or b for this wire is mu naught I over 2 pi r as well. And it wants us to find when it's equal to 0 everywhere. So my first point, we should have 2 points, right? Because we have when r is less than h and r is greater than h. So I'm going to start with when r is greater than h. When r is greater than h, I can just pick any point bigger than the circular wire. So I'm going to pick a point here. Let's call this x. So wherever I see an r, pretty much I'm going to replace it with this x. So when r is greater than h, I'm going to have mu naught I over 2 pi x, because my radius is now x, right? Like an arbitrary x, is equal to the field from the other wire, which is mu naught I divided by 2 pi, but it's not x because this other wire is at a distance w, right? So then this total distance would be w minus x, right? So w minus x, and then we just solve for x. So let me cross multiply. So 2 pi w minus x times mu naught I is equal to mu naught I 2 pi x 2 pi's drop, mu naught I drops, so I get w minus x equals x, w equals 2x, or x equals w over 2. And that is one of these solutions. To find the second one, we will need when r is less than h. So now I would have another x, which, let's say, I'm going to use blue. Let's say this is x. And then same thing, this total distance would be w minus x. So the same thing pretty much, wherever we see r, we're going to replace with the new radius, temporary radius we're making of x. So for r less than h, we have mu naught I r, in this case the r is x, divided by 2 pi h squared, and this has to equal to the magnetic field created by this wire, right? And again, the reason we're setting them equal to each other is because we want the total magnetic field to equal to 0. So we're trying to find at one point will the two regions in the circle cancel out with the field created by the other wire. And that one stays the same, so it's mu naught I over 2 pi w minus x. So I'm going to cross multiply again. So 2 pi w minus x times mu naught ix is equal to mu naught I, and then 2 pi h squared. So again, see what cancels out. 2 pi's cancel, mu naught I cancels. So we're left with, let me just distribute this. So wx minus x squared is equal to h squared, or x squared minus wx plus h squared is equal to 0. And this should look familiar, that we can use the quadratic formula. So a is 1, right? B, which is w, c is h squared. So we would have x is equal to negative b, negative is positive, so it's just w, plus or minus square root of b squared, which is w squared, minus 4a, which is 1, c, which is h squared, all divided by 2a, which is 2 times 1, so that's 2. And then in this case, we're saying that this solution is for when x is less than h. So if we said it was w plus the square root divided by 2, we're saying that it's w over 2 plus some other stuff over 2, right? And w over 2 is over here, but that doesn't make any sense because we're saying that this solution is for the region inside the circle. So there's no way that we can have a solution where it's outside. So that's why in this case we would only consider the negative part of the root, because we need this to be some point inside the circular region, not outside of it. So the two solutions would be this square root, and this is a w over 2, and at these 2 points is when the magnetic field, total magnetic field, will be 0. Okay, so now for the third question. The loop of a wire shown below is made of a wire with resistivity ρ and cross-sectional area A. Self-inductance is not ignored because it is given to us. Self-inductance is to be L. A nearby very long wire carries a current which varies with time. Okay, so the current generated by the wire is this. Gamma is a known constant, T is time. Okay, so we want to find the flux through the loop due to the long wire. So for this problem, we're going to need two equations. We're going to need, we're going to use Ampe's law to find the flux generated by the wire. It's a closed loop of B dot dr is equal to mu naught I. And then the second equation we're going to need is Faraday's law, which is the loop of E dot dr, again another closed loop, is equal to negative partial with respect to time That's a partial, it's not a 2. And then the flux of B, right? Just B dot ds. Or you could also see it as negative partial the flux of B. So let me use Amps law to find what the magnetic field is. So I'm going to create a loop, right? So this is my loop. Then I would get that B 2 pi r is equal to mu naught I, the current enclosed. So B is equal to mu naught I over 2 pi r. But the problem told us that the current generated by the wire is this, because it varies with time. So then it would be mu naught I naught 1 minus gamma t divided by 2 pi r. And then to determine the direction, if I put my thumb in the direction of current, right, and then I curl my fingers, when I curl my fingers are pointing to the left, right? They're pointing out of the page. So on this portion, they're pointing out of the page. And then if I were to curl it another way, on this part of the wire, it would be into the page. But we don't really care about that. We just care about where the wire is located. So the direction of this magnetic field will be out of the page, because my fingers are pointing out. So this is the magnetic field. And then we can use Lenz's law as well to determine the direction of the current. So in this case, we notice that the magnetic field is varying with time, right? So the magnetic field is going to decrease, right? Which means the flux is going to also decrease, which means B self, the magnetic field self-induced, is going to be in same direction as B, which is into the page. So then the current, if I put my thumb in the direction of the magnetic field, right, pointing out, current is going to be counterclockwise. So the current induced will be up here in the counterclockwise direction. And as I said in the beginning, but for these questions, you normally want to follow like steps. So you always want to try to determine the current. So find the magnetic field, determine the current by Lenz's law, and then from there, then you can start solving for the flux and whatever else it's asking for. So find the flux, well, it would just be the integral of B dot ds, right? This is flux, where B is not constant because B is changing with R. What I mean by that is if I create a loop, let's say I create another loop, right? My loop is right here, right? That is not going to have the same radius as if I created a loop here, or if I created another loop here, because the R is going to be changing, right? So our magnetic field is not constant, so we can't change the radius. So we're going to have to integrate over the magnetic field that we got, which is mu naught I naught 1 minus gamma t over 2 pi r. And then ds is the area. But again, if I draw the loops again, so say, let me just draw 2 loops for now. If I draw these 2 loops, right, the area is not going to be the same for the 2 loops, because the W in this case is changing, because one of them had a W here, one of them had a W here, and so on. So it's not the same. So what we're going to need to do is we're going to need to take a slice of W. And in this case, we'll call this distance, for the loop, we have this as R, right? So we'll call this R as well. Meaning this would have to be dr, and then d would stay the same, because that stays constant. But what's changing is dr. So then the area would be the length, which is d, times the width, which is varying, which is dr. And then we're going to go from we start at H, right? And we go to W plus H. So when I integrate this, I have 1 over R, so that just be ln. So everything else stays the same. Excuse me. So mu naught, I naught, 1 minus gamma t, d, divided by 2 pi, ln of W plus H minus H, but I'm just going to write it as a fraction with log properties. So W plus H over H. And this would be the flux created. So again, we didn't pull out the magnetic field because it changes with respect to R. R is changing as we climb up this box. And same with the area. Since the magnetic field is also climbing, the area is also changing. W is not always the same, because if we just left it as dW, that would be only true for 1 point pretty much, which would be like when we're at the top. But we're not. We're climbing up it. So we have to check. We have to take a little slice of the width, which is dr. So that's the magnetic field. And then part B, starting with some law, find the equation that could be solved for the current that flows in the loop. So we're going to use this law pretty much. Because right now we only found the flux. So let's take the partial with respect to time of the flux that we found. So the partial of B would be, if I look closely, I have 1 minus gamma t, right? So if I distributed everything, I would get like a bunch of numbers minus a bunch of numbers times gamma t. So the first group of numbers would cancel out because there's no t, right? And the second group, the derivative of negative gamma t would just leave me with negative gamma. So I'm going to have negative mu naught I naught gamma d over 2 pi ln of W plus H divided by H. H. So this is the partial with respect to time. And then part C is telling us to ignore self-inductance. In this case, part B wants us to include self-inductance. Recall that the flux by B self is plus or minus Li. And to determine if it's plus or minus, we will need to see if B dot dr is positive, which I actually didn't put here, so it's a mistake. So pretty much by convention, we always go in the counterclockwise direction for ds, meaning ds would point out of the page, which is not a rule. You don't have to necessarily follow this, but in the book, it always goes counterclockwise, so ds is always pointing out. And in this case, that's why b dot ds was positive, because ds is pointing out. Our magnetic field is also pointing out, so it's positive. I should also put B self here. B self is also out. So to determine if B self is positive or minus, it's the same thing. B self is pointing out, ds is also pointing out, so the dot product is going to be positive 1, so it's going to be Li. And then the partial derivative of the flux of B self is L, derivative of I with respect to time is di dt. So now I can put everything together. E dot dr is just going along the loop. So I need R, right? Because V equals IR. But I don't know R. But I know resistivity and know cross-section area is A, which I think this is given as well, right? Yeah, resistance is rho L over A. So let me just write that again. Resistance is rho L over A. Rho is given. A is given as little a. The length of the wire is, I have a D right? I have W. I have another D. I have another W, right? I have a D top and bottom, W left and right. So that's 2D plus 2W. It's the length. And I'm going to call this R. I'm not going to rewrite it. So that's the R that I'm talking about down here. I'm saying this is equal to negative by the law, right? Because I took the partial. I only took the partial. I didn't take the negative partial, right? This negative. So it'd be negative. Then I have another negative here. So negative mu naught I naught gamma D over 2 pi ln of W plus H over H. And then I would be adding plus L di over dt. And then you could distribute and simplify, but I'm just going to leave it like that. So again, the total flux, or I didn't write that actually. Flux total is flux of B plus flux self. In this case, it's not telling us to neglect flux self. So that's why we have to include it in our final equation. We have the negative here from the law. We determined that Li is positive because B self is pointing out by Lenz's law, and ds is also pointing out, so the dot product is going to be 1. We had to integrate for the flux because R was changing, R wasn't the same. Likewise, the area wasn't changing for each one of those loops. And we also determined it was positive because the B field created by the wire is out. ds is also out, so it's positive. And then for, I should say this is I1 because it's not the same current as this I. So I'm not sure if they would take off points for that, but that's not technically correct. So this would have to be I1. This would have to be I1. Then this current is I1. Yeah, I don't know how big of a deal that is, but it is important to note that it's not the same current as the one down there. Part C, it wants us to now solve for the current, ignoring self-inductance. So basically, we're going to use the equation we have up here, but this is going to equal to 0. So we're going to have I1 R is equal to negative mu naught I naught gamma D over 2 pi ln of W plus H over H. Negatives cancel, right? It's just plus. And then I just divide by R on both sides. So I1 equals to mu naught I naught gamma D over 2 pi R ln of W plus H over H. And recall that this R is not the radius. This R is the resistance that we determined up here. Rho over area times the length. Again, we have 2 D's, 2 W's. So that's the length of the box. So yeah, that's the answer. Ignoring self-inductance, that would mean this flux up here equal to 0. The partial of 0 is 0. So that's how we get this. And that's why for this one we had to include it because it told us, or it didn't tell us specifically, but the bottom one's telling us to ignore it. So this one we have to include it. Okay. Now, for this last problem, circuit problem, the loop of the wire shown contains a resistor R. So R is known. Self-inductance of the loop is known to be L. So we're probably going to have to solve with and without self-inductance again. Or maybe just with, I don't know. A uniform external magnetic field is created that is perpendicular to the loop pointing into the page. So B is pointing into the page. The magnetic field of the magnitude of the magnetic field varies. So we're given the magnetic field this time. That's nice. And it wants us to find the flux. So it's like the last problem again. But we don't have to solve for the magnetic field because it's given. So by convention again, I'm going to choose that ds goes counterclockwise. So ds will be pointing out. And I want to find the flux. So the equation I'm going to use for any circuit, again, it's a closed loop of E dot dr is equal to the negative partial, respective time, of the flux, which is B dot ds. Where this ds is the area, but the ds over here was the length. So I want to find the flux through B. Well, that's just going to be flux is equal to the integral B dot ds. So it'll be the integral. In this case, B is constant, right? It only depends on time. It doesn't depend on R. Excuse me. So that'll be B naught 1 minus gamma t times ds, which is the area, just h, or we're integrating ds, so I'll leave that as ds. So then I would have B naught 1 minus gamma t, integral ds is just the area, which is wh. And now, to determine if it's positive or negative, the magnetic field is pointing into the page. And by convention, I said that ds is pointing out of the page, so the dot product is going to be negative. So this is going to be negative. And if you made ds go, what is that, clockwise, then ds will be also pointing into the page, which would mean your answer would be positive. But again, I'm just making ds always go counterclockwise. So ds is always pointing out because that's how the book does it, and that's how the answer key has it as well. So, but you can do it however you want. As long as your signs are consistent, you're fine. So now for part B, we want to find a differential equation that could be solved for the current that flows in the loop. So, like the other problem, we need to find the total flux, but I need to know what B self is. So that's where Lenz's law is going to come in. So if I look at my flux equation, as time goes on, right, the magnetic field goes down, right? So that means my flux is also going to go down. It's going to decrease. So then B self would be in the same direction as B, which is into the page. So current is, if B is into the page, current will be counterclockwise. Clockwise. So current will go this way, which would be the opposite way of how we define our loop, which is kind of dumb, but that's how the book did it, right? So it's gonna stick with it. So now I can find the if the induced flux is positive or negative. So induced is plus or minus Li. B, or B self is the same as B, right? So this is B self. B is going into the page. ds is coming out of the page. They're going opposite directions. Dot product is going to be negative. So it's going to be negative Li. And then the partial of this, flux induced, will be negative L di dt, right? Same as the other problem. And then we should also find the partial of this flux. Oh. So that would be the partial of negative, or if I distribute it again, right, I would get a bunch of numbers minus a bunch of numbers times negative gamma t. So the negatives will cancel. Now I'll just be left with gamma. So B naught gamma WH. So then my equation would be, if I go around my loop, right, I go into the resistor, but current's going the other way, so it's going to be negative IR is equal to negative by the law, right? Because again, I only found the partial derivative of time, but I still have a negative that I'm going to distribute. So I would have negative B naught gamma HW, and then what else? Minus L di dt. And I can go ahead and simplify this a little bit. I would get negative IR equals negative omega naught gamma HW minus L di dt. Oh no, what am I doing? How am I distributing my negative? So this would be positive. The magnetic field would be negative, yeah. Oh. So if I move everything over, I get negative IR minus L di dt equals negative B naught gamma HW. Just divide by negative 1 because they'll have negatives. So IR plus L di dt equals B naught gamma WH. And it says that could be solved, so we don't actually have to solve this yet. It's just one equation. But part C wants us to solve it. Solve the current that flows in the loop as a function of time given the initial condition t is equal to 0 and the current in the loop is 0. So if we look at this equation, we need to recognize this is a non-homogeneous differential equation, first order. It's not homogeneous because it's not equal to 0. It has some random junk on the side. If you took differentials, you could use integration factor, but that's a little annoying. So we could just use it how we're taught in class since it's not a prereq. So what we're going to do is we're going to say the current as a function of time is equal to current at a particular solution plus the homogeneous solution. So for this one, we're going to have in steady state d dt is equal to 0. So anywhere we see that's going to be equal to 0. So solving for IP right now, right? I would get IP R plus L, but then in steady state, the derivative of this will be 0. So times 0 equals B naught gamma WH. So the particular current will be B naught gamma WH divided by R. It's pretty easy. Then the next one's where it's a little more challenging. For IH, what we do is we assume that IH has a solution of alpha e to the negative beta t. And if you took differential equations, again, you would know where this is coming from, but if you didn't, it doesn't matter. You just need to follow the steps. So what we're plugging this in is to the original equation. But for this homogeneous solution, this portion here in red, it's going to equal to 0. Right? Homogeneous equal to 0. So if I just plug that in, I would get alpha e to the negative beta t times R plus L, and then the derivative of this, which is itself, alpha e to the negative beta t, times chain rule, which is negative beta. And again, we're assuming it's a homogeneous solution, so it's going to equal to 0. So we need to solve for beta in this step. So the e's can cancel. E's cancel. Alphas cancel. So I'm left with R minus beta L is equal to 0. Negative beta L equal negative R, or beta equals R over L. And then when we get to this step, we need to combine it. So we combine it, whatever we got into this equation in green. We plug in our initial condition, which here is t equals 0, current in the loop is 0. And then with that, we can solve for beta, and we get our answer. So let me move this over here. I of t is equal to IP, which is B naught, gamma WH over R plus IH. IH is this, right? In the red box, this is IH. We've solved for beta, so I'm going to plug in beta, but we don't know what alpha is yet. So it's plus alpha e to the negative beta. B is R over L. T, and we know that time equals 0, so ISO 0, so what I mean by initial condition. Current is 0, so this has to equal 0. So 0 is equal to B naught gamma WH over R plus alpha, and then e to the 0 is just 1, right? So just times 1. So then alpha would be negative B naught gamma WH over R. Should be a negative there. So then if I plug everything together, I get current as a function of time is B naught gamma WH over R minus B naught gamma WH over R e to the negative R over LT. Or how the answer key has it, oh, I have like no room, so let me just move it over here. The answer key has it as I sub t is equal to B naught gamma WH over R, then it's 1 minus e to the negative R over LT. That'll be the answer. So for these equations, when you have a non-homogeneous differential equation, which is what we have here, because this does not equal to 0. So non-homogeneous, genius, I don't know, I'm assuming it's spelled like that, which means it's not equal to 0. You have to follow this process. So you have to assume that it has a solution of IP plus IH. IP is in steady state, so anywhere you see DDT or all that stuff is equal to 0. So that's why we said IR is equal to beta naught gamma WH. And then for IH, you need to assume that it's alpha E to the negative beta T. You plug in this anywhere you see I. We saw DI/dt, so we had to take the derivative, and then we had the chain rule, it's negative beta. We set it equal to 0 because that's the homogeneous part of the solution. We solve for beta. Once we solve for beta and IP, we plug it into this green box equation, which will give us this. And then we use the condition and gives us to solve for alpha. In this case, it's at t equal to 0. The current is 0. So once we plug t equal to 0, we solve for alpha. And then once we get alpha, we put everything together and get the final answer, which is boxed in. And again, Lenz's law is really important because we have to use self-induced in here. And it also helps because it tells you the direction of the current, because we use Lenz's law to determine current here. And we also use Lenz's law here to determine the current. So really important to know. So I hope that helped, and good luck on your exams.